It's very nice to see that many people interested in our work. So I welcome you once again. So what we did is, first I'm going to start with a little bit of introduction about me, my research project, why we did building segmentation, and what is regularization, why it is important, or can be important, and then our final product, which will be, hopefully, the QGIS plugin. So we are located in Bergen. It's a very nice city, a lot of rain. If you like rain, come visit us. When it's sunny, no one works, so we just enjoy life and try to have fun. But in the winter, we work a lot. At our department, we have a bachelor program in civil engineering, in land administration and land surveying, and a master program in land management. So my research project focuses on finding methods to correct mistakes in the Norwegian cadaster, because there are many, many mistakes. There are circular properties, as you see on this image, which are properties without correctly mapped boundaries, and we are trying to find solutions how to map them with AI. I use open source tools for my work, mostly QGIS, Postgres get data from databases, and Python, PyTorch for writing AI models to do my work. And this is an example of a Voronoi diagram suggestion to improve the Norwegian cadaster. As you can see, these buildings or like properties we don't know where the mapped properties are or the boundaries. So Voronoi diagrams can be an interesting thing to provide some solutions. Some things we are trying and failing to do is making cadastral document detection systems from historical measurements, including natural language processing, AI-based cadastral mapping, and AI-based georeferencing. So this is what I still need to do. Why is our work important? Because correctly mapped property boundaries are very important in today's world. If the neighbors don't know where their boundary marks are, they don't know where their buildings are. And this leads to legal issues. And this is an example where the neighbor cut the other neighbor's house in two. So there are some people that are very serious about their buildings. So yeah, this can happen. And there's also mistakes, as you see here, yellow, the properties. And here, the AI needs domain-specific knowledge, not just getting what we see from an image, but we need to provide reasoning and the ability to decide logical reasoning altogether. And yeah, currently we are stuck in this phase, how to put this together and detect buildings, detect property boundaries from historical maps, visible property boundaries, and yeah, it's a lot of, it's a mess, and I'm lost most of the times. Yeah, so as you can see, or already know, buildings can be cut in two, but we can also detect them with AI. And this is my plan for my PhD. So we want to detect the buildings, improve the detected building footprints, and then check which buildings intersect with the property boundaries. And then we want to detect the property boundaries from documents, from aerial images, satellite images, and so on. And the last phase is automating the cadastral mapping from historical records, and then also suggesting improvements using Voronoi diagrams, which are very interesting thing to do, because we also see them in nature following certain tiles and formations. Okay, so this building segmentation workflow that we did, I wanted to see what is possible to do and which methods exist to improve the building footprint further on. And I didn't want to use polygon simplification methods. Instead, I tried to find a solution that someone already did with a CNN, a convolutional neural network, and then put it all together in an end-to-end way, so you can run my Jupyter notebooks, and hopefully they will work for you too, not just for me. And our research questions were basically this. Does this regularization further improve the segmentation or the prediction accuracy of the building? Does it also improve the geometrical shape, so we get more correct buildings at the end? And also, if the footprints look more useful for further application? And can we apply these vision transformers, which are like a new kind of networks or neural network models that we can apply for binary semantic segmentation? And then how can we develop this workflow into like a fully working QGIS plugin that users can use? Because it's very nice to do practical work, not just some theoretical. I mean, it's also nice to do theoretical work, but practical work counts and it's important. So we have to share it and yeah, provide it with others. And the last question is just, we already know that it's possible to do everything with open source, right? That's why we are here. And more people need to know that. So not a lot of theory, just a little bit. So as you know, there is AI, there is computer vision, and these are the 4 main tasks of computer vision. This is basically the science of teaching computers how to recognize images, how to extract information from images. And this is what we were working with semantic segmentation, where the image gets recognized and each pixel gets labeled by its class. So in this case, each pixel gets a semantic label, and because we were just trying to find buildings from aerial images, we just have one class, building. So it's a binary semantic segmentation method, and our result is just a building at the end. What are convolutional neural networks? They are grid-like structures, artificial neural networks, special type of artificial neural networks that use a grid-like structure. It can be images, time series. They just need to have a grid-like structure as an image, for example, a matrix. And the input data is processed to many convolutional layers, which do filtering operations, do matrix multiplications, and then try to extract edges and different colors and so on. And each convolutional neural network has convolutional layers, pooling layers, and fully connected layers. And at the end, we get like a classification output if something belongs to a class or not from the image. Yeah, so they are very popular, are becoming very popular. And this regularization workflow that we tested and tried works with generative adversarial neural networks, which is a special type of neural network that is generating new images from already existing data. So you can, what is basically the idea here? We have a generator that generates fake images from already existing data, and we have the discriminator that checks if the image is correct or not. And they are playing a game, and when they are like agreeing that the image is good, they we get a result. So the generator model trains and generates new examples, and the discriminator tries to classify examples as either real or fake. And you can also translate images. For example, we can train the neural network with Van Gogh's paintings, and we get Vincent van Gogh because it's generative adversarial neural network. So this is a nice example of making fake art, if you want, and you can sell it for high price, hopefully. And then the vision transformers. So this is like complicated theory, but I'll not spend too much time here. You can look it up. There are like classification algorithms and architectures that use this self-attention mechanisms from natural language processing. So natural language processing means recognizing text. And what they do is they do patch-based learning. So all these patches have to be one by one next to each other, and they are processing data in like a diversified manner going through. And the problem with these vision transformers is that they require a lot of data to achieve good performance and are also prone to overfitting. So we applied these 3 vision transformer models here: UNet-Former, FT-UNet-Former, and DCSwin, which is like a transformer-based architecture also. You can read more about it here if you're interested, and also in the publication. And then we found GeoSeg, which is an open source semantic segmentation toolbox where we got the models, these vision transformer models, changed the Python code and made it to a binary semantic segmentation workflow with PyTorch. And so we only got the buildings, because here you can see that we have like a multi-class classification task. We were just interested in buildings. And then we come to the regularization. So now you understand what regularization does. So we have an input image, teach the algorithm how to recognize it, how to recognize buildings. We got the segmentation. This is predicted with the AI. And then with the regularization part, we further improve the building footprints. So this here, for example, looks a little bit rounded, but here it has become a correcter, better mathematical polygon shape. So this is useful as the last part in doing image segmentation for buildings or other things. So we found this nice generative adversarial neural network method that these researchers published on GitHub, and we applied it on our own data, or another data set and another use case, and made some modifications for the semantic segmentation part. It also works with instance segmentation, not just semantic segmentation. And how this works is that the generator learns the mapping function from the segmented building footprints that we provide, and then from the training set, it also learns the ideal buildings, what it should be, right? So we get like two different data, and then the generator generates better representations of buildings, and then we are happy at the end, hopefully. So our methodology was like this. We trained our data on the MapAI dataset, which is a publicly available building dataset from Norway. It has been published last year in December. We applied these for models, a basic unit just to check how good the basic unit is, and then this vision transformer architectures. Then we made some predictions and provided the regularization framework at the end. And this is the dataset. It has training samples derived from aerial images, a LiDAR training sample, and also a mask sample, which is basically the ground truth of the image, as you can see. And it's also possible to combine these three together, like to do LiDAR-based classification and so on. Okay? When we evaluate the results, it's very important to check the accuracy, of course, by using metrics, the completeness of building extraction, and the effects of building boundary regularization on the extraction. And also we need to handle special cases of building. So you see this is a mistake, right? There is no building here, but the AI recognized it. If we have a forest, of course, there is no building because we don't see through the forest. And these are our results. Of course, they're not good, but yeah, we need to make it better. It also depends on the test set. So if the test set has like a lot of very strange buildings, and you didn't train your algorithm that way, and didn't use data augmentation techniques, then of course you will not have the best results. But it works for rural areas where there's a lot of overlaps between buildings. And then you can see that the regularization at the end already improved it, made it more geometrically correct in the end. So that's what I wanted to test and wanted to present. And then the last thing is the QGIS plugin, which I designed it so that you can import an image, and you can regularize it, make it more appealing, and at the end you can vectorize it and save it as a TIFF or a geo package or another different file. So the useful thing here would be to just do this on a vector data, not raster data, but vector data, because now when we are like converting between rasters and vectors, we lose some data. So yeah, that's the next step where someone can help me do it and collaborate with us. So because sharing is caring, here are all the QR codes. This is my contact information, the segmentation workflow repository in GitHub, and the QGIS plugin repository where I'm developing the plugin and sharing the code with you. So hope you liked the presentations, and yeah, we have some time for questions now. Thank you.